Let's add a couple of points about global potential for carbon dioxide removal. This is by Tim Lenton, who works a lot on Earth system issues. We have been looking at this kind of figure for a few podcasts now, where we are talking about global greenhouse gas emissions and warming scenarios. So here is the total CO2 equivalent. So that includes converting methane, N2O, HFCs to CO2 in terms of global warming potential, so that we can look at total emissions reductions. We look at the historic trajectory we are on, and then we look at the potential for warming with business as usual, what we call no climate policies, where the current climate policies are expected to bring us, and what the additional pledges under Paris Agreement are doing, and then where we actually need to be if we want to hit the 2 degrees centigrade or 1.5 degrees centigrade targets. We haven't said much about the uncertainties in these numbers in terms of the amount of CO2 to be drawn down, but nonetheless it's been a point of contention. For example, if we look at the surface temperature change since 1850 to 1900 base period, and we look at the cumulative carbon since 1876, in terms of gigaton CO2, then we see essentially a linear relationship where there are multiple pathways here shown in terms of different models, so I won't go into that. But the main point I want to make here is that there is a near linear relation between cumulative carbon and warming. So this has been used to argue that if we take our emission trajectories and then look at the amount of CO2 that is needed to be removed, then we can calculate the number of years left to save the world. This is argued to be fallacious, if not dangerous, by some, including some social scientists, and I happen to agree with it. So let's look at that here. Remaining carbon budget for a 66% chance of less than 1.5 degrees centigrade by 2100, and you can see that did I cut off this figure? I hope not. Let me make sure it's okay and then come back. Sorry about that, I had screwed it up, so I have fixed it, and now continue. Remaining carbon budget for a 66% chance of less than 1.5 degrees C warming. So we are looking here at gigaton CO2, and you take present value as 0, doesn't matter which year, but you go back here, which means we actually have to draw down carbon, which means we have already shot past the target of 1.5 degrees C by 66%. And you look at the years of current emissions. So you got 0, 10, 20 years, or you have minus 10 years, and here are the different models, different studies, which either used Earth system models, which are much more comprehensive, climate models with carbon cycle, but they kind of simplify the socioeconomics, energy sector, food sector, transportation, and so on and so forth. These are combined observations and Earth system models in these blue colors. You can see that they are just dots here because they don't always give a range. It depends on whether the range came from using multiple models or multiple scenarios, because this is the future. Integrated assessment models are simpler models where climate is given in some form or represented in a very simple way, whereas other sectors like transportation, energy, economy, population, and so on are represented in much more detail than in the Earth system models. So there is a choice made there. The point I want to make with this is that the estimates are all over the place. You can see that Earth system models are down here at 118 gigatons, or ranging from already having gone past, so minus 192 to 243 with the median value of 67. And there are different scenarios shown here and different estimates. So one has to be very careful in translating remaining carbon into any kind of years remaining at current emission rates. That uncertainty must always be kept in mind. Remembering that, we look at briefly what is the global potential for carbon dioxide removal. These are the various methods considered by Tim Lenton: direct air capture or bioenergy crops with carbon capture and sequestration with some geological CO2 storage. We already talked in the last podcast about the potential timescales of storage. So here are biocrops, including agriculture, and here you have afforestation. So you're doing pyrolysis and biochar in soils that we talked about, or we can also grow biomass and then just bury it. This is another idea of hiding CO2, but we already said that this would take a lot of land. Plus, this is highly inefficient in terms of trees capturing carbon, right? Bioenergy, macroalgae and microalgae. So this is also considered with carbon capture and sequestration. So this is also for geologic storage. Enhanced weathering. We have talked about the olivine type of rocks which can be ground up and put on land, and since they are ground up, the same amount of rain and CO2 is going to have much faster weathering rates than the slow geologic timescale weathering that occurs naturally. So you combine that with alkalinity enhancement that we already mentioned in one of the podcasts, where you are also have to worry about whether other nutrients are available, and then how much additional carbon production and carbon export actually happens. So you need the organic carbon to be taken into the sediments, so that or you put the additional dissolving organic carbon deep in the ocean so that it stays there for a long time. So the residence times are very different as well depending on where it is. Okay, considering all these methods, the estimates by Tim Lenton for total physical carbon dioxide removal flux potential in petagram carbon per year on different time horizons. He compares estimates of other studies as well in the chapter, which I'm not going into. I'm just adding these details to the book we used, The Planet Remade. So this is just to give you some additional points. So remembering that. At present, plant-based CDR, it's 0.75 to 1 petagram carbon per year. By 2050, it can be expected to be ramped up to 2.3 to 5.75. So under drawdown, the course that I have on my channel as well, we go through many such methods and numbers as well. I'm putting here this again in the context of geoengineering the climate system. Okay, by 2100, it's 5 to 20 petagram carbon per year. So we are talking about reaching reasonable levels by 2100 when compared to the amount of CO2 drawdown needed for hitting the 1.5 degree C target with 66% probability. So this is algal based CDR, 0.9 to 1.4. By 2050, 1.6 to 2.6, and then by 2100, 2.9 to 4.2. Anytime we make these future calculations, obviously there are many assumptions involved, many scenarios, many availability of resources to do these things. So this is why these are called flux potentials, what is ideally accomplished if we have everything being the same. Alkalinity enhancement based CDRs. Right now there is zero potential. By 2050 it can ramp up to 0.5 to 0.8 plus maybe direct air capture, and by 2100 1 to 1.6 plus direct air capture. So total CDR then of all these methods is at 1.65 to 2.9, 4 to 9 by 2050, and 9 to 26 by 2100. All questions remain about the cost of, for example, grinding up rocks and spreading them, how to do alkalinity enhancements, and whether it can be sustained and feasible, at what scale it happens, etc., etc., are all kind of the questions that don't really go away. Okay, I'm going to leave this here and then come to cooling of the earth with crops.